Hello friends, we are starting one of the most scariest topic for the students, microprogrammed control unit or microprogrammed controller. Now from the name microprogrammed control unit, don't get scared. We are not going to perform any kind of coding here like C, C++ and Java. So why this approach is called microprogrammed control unit? Why we are going for this approach we will see in today's lecture. And trust me, this topic is not that difficult as students feels like. Just you need to practice some few examples, then you will feel this approach is also as easy as your hardware approach. So we need two videos to complete the whole microprogram control unit. So we'll have two parts for that. In this part, we'll see the basic of microprogram control unit, and in the next part, we'll see how to design a microprogram control unit for Booth multiplication, which we have seen for hardware approach also. So let's start the discussion. In our last few videos, we have discussed about the hardware approach to design a controller or control unit, right? And we have seen a specific application which was Booth's algorithm, and we have seen how to design a hardware control unit to perform Booth's multiplication. Now in today's video, we'll start a new approach to design a control unit. We'll start microprogrammed approach to design a control unit or controller. Now, from the name microprogram, don't be confused or don't get scared. We're not going to perform any kind of coding operation here. Understand? We're not with this Java, C++, Python, no coding is required here. So don't get scared by this term microprogram. Now why it's called microprogram? Let me explain. If I ask you what is program, what will be your answer? A program is nothing but a set of instructions. Fine. Now, as the same way, if I ask you what is microprogram, then your answer should be a microprogram is nothing but a set of micro instructions. You understood the difference? Program is the set of instructions and microprogram is the set of micro instructions. Now what is micro instruction? We know instructions. What is micro instruction? Suppose I want to add, say I have an instruction like say add r0 comma r1. This is an instruction, we know, right? Add r0 comma r1, and I know this add r0 comma r1 will perform r0 equals to r0 plus r1 for me, right? For that I have written one single instruction, add r0 comma r1. Now whenever we write some kind of instructions, this is not like within a second your processor will execute this thing, right? So what is the approach? Actually, whenever you write this instruction add r0 comma r1, then the data will be loaded from main memory to register r0. Then the data will be loaded from main memory to the register r1. Then it will be going back to arithmetic and logical unit. Then the operation, the arithmetic operation will be performed. Result will be stored back to your register, right? There are multiple steps actually. To perform a single operation, what was the main operation? Main operation was to add two numbers. This was the main operation. Now, to perform this simple operation to add two numbers, there are multiple sub operations, right? So many things I have to do. I have to load, I have to transfer to ALU, then arithmetic will be performed, then it will be transferred back to register. So many micro operations are there. So these small operations are nothing but micro operations. So I hope you understood what is micro operation, right? Now, for any micro operation, whatever code you write, whatever instruction you write are known as micro instruction. Means small instruction. You have a big instruction, you divide or you partition your instructions into multiple small tasks. Those tasks or those set of small instructions are nothing but micro instructions. I hope it's clear for you. Now microprogrammed are nothing but the set of micro instructions. What is micro instructions? The instructions that can perform some micro operations. What are the micro operations? Small operation. Like say I want to simply load something from this to this. Fine. I want to move something from this to that. So small operations are known as micro operations. Fine. Now, whenever we talk about microprogram control unit, I hope it's clear for you what is microprogram. Then we'll go ahead. The next thing is, whenever we go for microprogram control unit, we have to know some of the important terminologies which we will use again and again in future. So you have to note down all these terminologies. The very first terminology is control word. This term we'll use again and again. Now what is a control word? Control word, let me explain. So remember, whenever we designed a control unit using hardware approach for Booth's algorithm, what we did? So we know that for Booth's algorithm, we have seen already, we need C0 to C9, total 10 control signals I need to generate to perform the operation, if you can remember. If not, then please go back and watch the video. Now, what we did in hardware approach, one by one we generated the signals, right? Say in clock pulse 1 or first clock pulse, I need C0, C1, C2. I have generated C0, C1, C2 and I have sent the signal to the particular hardware. Done. In the next clock pulse, I was thinking which control signal I need. So I know in the second clock pulse I need control signal number 2 or 3. So I will generate control signal number 2 or 3 and then I will send this particular signal to that particular hardware. This is how we have performed the operations, right? So whenever you need some control signals, you generate it and send it to the particular hardware. That is how we work in hardware approach. Now in microprogrammed approach, there is a twist. We won't follow the same approach here. Here what we do is, initially we identify how many control signals I need throughout the operation. First I will identify how many control signals I need. So we know for Booth's algorithm I need 10 control signals, C0 to C9. Now, unlike our hardware approach, here what I will do is, I will generate all these control signals first. Fine, all the control signals I will generate first and then I will store somewhere. Fine, so I will have all the 10 control signals somewhere stored, and whenever necessary I will just activate the signal. Say in clock pulse 1 I need control signal number 0 and 3. Fine, I have all the signals with me, 0 and 3 I will send. In next clock pulse, say I need to send the control signal number C9. Fine, all the control signals I have, just send it or just activate it. You understood the difference? In hardware approach, whenever necessary you generate the signal and send it. But in microprogrammed approach, you generate the signals first, store it somewhere, then whenever necessary just activate. Don't generate whenever necessary. I have already generated, it's already there somewhere. You need it, take it. You understood that? Now, the set of all control signals which are necessary to perform an operation. For example, for Booth's algorithm, we know we need C0 to C9. So this set of all control signals which are necessary to perform a specific task are known as control word. You understood the term control word? Fine. Next important terminology you have to understand is control memory. I told you we have to generate the control signals first and then we have to store it somewhere. Where I will store? I need some memory to store my control word, right? That memory is nothing but control memory. So control word and control memory, these two terms you have to remember. Other than that, micro operation, I already told you what is micro operation. Now we understood what is micro instruction, we understood what is control word, we understood what is control memory, I guess. Fine. Now all micro instructions have two important fields. Remember, whenever you are writing some micro instructions, in the micro instructions you will have two major fields. What are those? Number one, control field. This control field is nothing but the set of all control signals. When you need all the control signals, you will store here in control field. This will deal with all the control signals. And the next field is next address field. Next address field is nothing but a field, address field, which will tell you which is the next micro instructions you have to perform. So initially you have executed micro instruction number 0, just like our instructions. What do we do? Initially we execute the first instruction, then next, then next, then next. If there is any branch or looping, then we will go back to, or jump to that particular instruction and so on, right? Here also we do the same thing. We'll execute the first micro instruction, second, third, like that, until and unless we get any jump or loop or break, then we'll continue sequentially. If we get anything, then we'll jump. Now who will tell me where to take a jump or whether it is sequential or what? This next address field will tell me what to do, whether I shall go sequentially or take a jump. How next address field works. Fine. Now let's see the block diagram of a microprogrammed control unit. Now don't get scared by seeing this very complex diagram. I'll try to make this diagram very simple. Just pay attention. This block diagram was proposed by Wilke. Wilke is a scientist, and long back in 1950s he proposed this block diagram for microprogrammed control unit. Now how it works, how the microprogrammed control unit works, you will understand from this block diagram. Please pay attention and don't get scared. Suppose this is a random example he has taken. This is not a specific task like Booth's algorithm. A random example he has taken. Suppose for any specific task, I need total 5 control signals. Please pay attention. For any specific task, I need 5 control signals. So I have C0, C1, C2, C3, C4. Fine. I know in microprogrammed control unit, I shall have a control memory where I will store all the information about my control signals, right? So this big block is nothing but the control memory. Inside control memory, I will store all the important information about my control signals. Fine. Now what I said, for example, I need only 5 control signals to activate for any specific task. So C0, C1, C2, C3, C4. These are the control signals I already have generated and I have stored to my main memory. Not main memory, control memory. Fine. Now, if you remember in Booth's algorithm, how many states we had? We had something 8 or 9 states, right? T0 to T8. 9 states we had. So for example, for this particular application or program, I need total 8 states to be executed. State means in each clock pulse, I will decide how many control signals I need. Fine. Since I have total 8 different states, so what I will do, I will use one decoder 3 to 8. Where this side I will have 8 different states. State number 0, 1, 2, 3, 4, 5, 6, 7. So if you have any confusion about states, you can go back and watch my previous video where I discussed about states. Still, state are nothing but in each clock pulse, what are the set of signals or what is the main operation you want to perform? That is nothing but a state. So for the specific task, I have total 8 states and total 5 control signals I need to overall perform the operations. Fine. Now suppose in state 0, means in clock pulse 0, in first clock pulse, say I need to activate only 2 control signals. I need only 2 control signals, C0 and C1. What I will do is, in state 0, this is state 0, so I have all the control signals which are connected with all the states. It will be connected with all the states. Since these signals are already ready, what we will do is, whenever I need it, I will just on it with the help of some fuse. If no need, then I won't connect it with any fuse or any switch. See here, for state number 0 or in clock pulse 0, I will activate 2 control signals randomly I have taken, which is nothing but C0 and C1. So what I am doing here, I am using 2 fuses to connect C0 and C1 for state number 0. Similarly, the next clock pulse, when I will execute state number 1, say randomly I need C0 and C3. So C0 and C3, I will just on it. You can make a cross also. Fine. Similarly, in state number 2, I need C0 and C3. So just on this thing. In state number 3, I need C1 and C2, just on it. So like this, in all the states, I have all the signals. Whenever necessary, just on it. I hope this decoder is clear for you why I have taken 3 to 8, because I have total number of 8 different states. So I have taken 3 to 8 decoder. If the number of states are more, then I have to take 4 to 16 and so on. And why I have taken 5 different control signals? This is just a random example. I am assuming that there are total 5 control signals. Fine. And what are these fuses? I think you understood. And this field is known as control field. Fine. Set of all the control signals. Now this part is clear, I think, for you. Now, as we told you in the previous slide, that in each microinstruction, one more important field we have, which is next address field, right? This next address field will tell me which is the next state or next microinstruction you have to execute. Fine. See here, I have a next address field. Now, can you tell me how many bits I need to store the next address for my states? Yes, 3. Why? I have total 8 different possibilities, right? Now, which state I will activate in the next clock pulse? To decide that how many bits I need. 3. 2 to the power 3 equals to 8. So to select any one of this state, I need only 3 bits. For this particular example, that's why I have 3 bits here to decide the next address. Fine, these are the this is the next address field. Now see here how it works. In clock pulse 0, I am executing T0 or state number 0, and I need these two signals I am activating. Now what is the next state or next micro instructions I will execute? This field will take. See here, what is the next field here? 0, 0, 1. This connection means 1, no connection means 0. Means when I am executing the 0th state, the next state should be 0, 0, 1. Means the 1, this is state number 1. So next time it will execute this one. When I am executing the when I am executing the first state, the next state I shall execute is 0, 1, 0, 0, 0, 1, 0, 1, 0. Means second one. When I am executing second, the next state should be 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. So sequentially I am telling my decoder to execute the next state. So this is how it will tell you decoder which one is the next state. You understood that? Now suppose there is a jump or some other conditional branching, unconditional branching. I cannot always execute sequentially, right? In my program I will have some conditions, I will have some looping, jump, so many things, right? Now who will decide that? For that I will have some external hardwares I will have to use. Through these hardwares I will send the signal to my next address field that there are some conditions. So if this is the condition, then don't execute sequentially. See here, after 101, it's not 110, it's 001. Means here again I have to go back to state number 0. Why I am going here? Because of some conditions or branching or looping. From where I'll get that condition, branch or looping? Through these external hardwares. Now when these conditions are satisfied, I'll go to state number 1 again. Fine. So this is how this next address field works. I hope this field is also clear for you. This next address field, control field, what is control memory, why this external condition is here, why this decoder this side. I think this side of the diagram is very clear for you. Fine. Now we'll come back to left hand side. As I told you, this 3 address line will be connected to my decoder, but if you see here, these lines are not directly connected to my decoder, right? It's not that I have this line and directly connected. I have some multiplexers in between. Now what is the functionalities of this multiplexer? I am using 2 to 1 multiplexer, and everywhere I am connecting the signal from the next address field, right? 1 line I am connecting to 1 multiplexer, 2:1 multiplexer. Now since it is 2:1 multiplexer, I need one selection line also. This is the selection line. Fine, this is the selection line. So by default this selection line is 0. This selection line is 0 means the input line 0 will work. What is my input line 0? This input line 0 is nothing but the next address field. See, everywhere it's connected with 0 input field only. So by default your selection line is also 0. So it will take the address whatever sending by your next address field. Now why we need this multiplexer? Sometimes it may happen that you are running your code fine, but forcefully user want to change the sequence. Forcefully, externally you want to change the sequence. No, I don't want to execute this now, I want to execute this. Though your address field is giving this state to be executed, but you don't want that for any reason. You want to skip that, or you want to jump somewhere forcefully. That time in this multiplexer you can put your own address also. Say you after state number 1 you want to go for state number 7 directly for any reason. So you have to put the address for 7 here. Fine, 1 1 1 if you give, then 7 you will go. Say 6 you need, so what you will do? 1 1 0, 6 it will go. Now when you are putting some signals here from external lines, then your selection line also will become 1. 1 means the second input of the multiplexer. And what is the second input? It's the external input which you are giving or you are providing. Fine. And then these signals are connected with D flip-flops. Now what is the functionalities of D flip-flop? I think you already know very well. In your digital system you already got this D flip-flop concept. So this is how the microprogram control unit works as per the Wilkes diagram. Fine, this diagram is Wilkes diagram. I hope this is clear for you. Now the next important thing is the length of microinstruction. How lengthy your microinstruction will be depend on some factors. There are 3 major factors. Based on that, you can say how lengthy your microinstruction will be. First one is the degree of parallelism. What is the degree of parallelism? Means in one micro instruction, how many control signals you are using at the same time. Suppose you have total 4 control signals, C0, C1, C2 and C3. And in one micro instruction only, you are using all the control signals, say X, Y, Z, C0, C1, C2, C3. So all the control signals you are using in one micro instruction. Means what you are doing here, parallelly you are executing many control signals at the same time, right? In one micro instruction. If you do so, what will be happening? The length of micro instruction will be increasing. Of course, if you are executing all the micro instruction, if you are executing all the control signals in one micro instruction, then you need more bit of information to store, right? The length of micro instruction will be more. If you are using less control signals in each micro instruction, then length will be less. So length is more means degree of parallelism is more. Length is smaller means degree of parallelism is smaller, less. You understood that? Now, if you are using more degree of parallelism, one advantage is your overall micro program will be smaller because all the control signals you are using in one or two lines only you are using everything. Fine. The micro program will be smaller, but micro instructions will be lengthier. Fine. What is the second one? The second thing, important thing which affects on the length of micro instruction is the control field organization. How you are organizing your control field. Now there are multiple ways to organize your control field. What are those? Let's see. Suppose you have 4 control signals, C0, C1, C2 and C3. These are the 4 control signals you have to use throughout the operation or throughout the application. Now how you can organize these control signals? There are two major ways. One is, what you can do? You can assign 1 bit for 1 control signals. Whenever you need it, make it 1, otherwise make it 0. Say you want to use only C0 here, so put 1 and rest all are zeros. So C0 will be activated. You need C1, put 1 in C1, all other zeros. You can activate C1. So like this you can organize all the control signals. 1 bit for 1 control signals. You understood that? If we do so, can you see any advantage? Yes, the advantage is at the same time I can activate more number of control signals. If I have more number of out buses, then what I can do? If I need C0, C1 at the same time, so I will make 1, 1, 0, 0. So these two will work. Say I need all, so 1, 1, 1, 1 I will make, so everyone will be activated. Means at the same time degree of parallelism is more, right? At the same time I can execute, or I can execute more number of control signals. This way of arrangement is known as unencoded arrangement of control signals. And also this approach is also called horizontal approach. Horizontal approach for micro instruction. Fine. Now the advantage and disadvantage I told you. Advantage is degree of parallelism is more. Disadvantage is you need more number of bits to store the information. Suppose you have 16 different control signals, maybe 1000 control signals you need for your program. You need 1000 bits, right? It may be 0 or 1, but you need 1000 bits to store 1000 control signals. So you need a huge memory for that. So this is a major drawback actually. So what is the alternate way? The alternate way is to arrange in encoded form. Encoded form means, see here, say I have total 8 control signals, forget about 2, 3. I need 8 control signals in my application. So in encoded, how many bits I need? 8 to represent my control signals, all the control signals, right? But in encoded, what we can do is, we'll use a decoder, 3 to 8 decoder. Now to select any one of these control signal out of 0 to 7, total 8 control signals, how many bits I need? I need only 3 bits, right? 0, 0, 0 means first control signal, 0, 0, 1 means second control signal, 0, 1, 0 is third one, and so on. You understood that? So see, for 8 different control signals, I need only 3 bits to store the information. So like this, what we are doing, we are saving the number of bits. For the large program where I need more number of control signals, this is really helpful. This approach is known as encoded approach, and also this approach is known as vertical approach. Please remember. Now can you tell me any advantage and disadvantage? Advantage is I am saving the number of bits. I need less memory to store this control field information. Disadvantage is I cannot activate 2 control signals at the same time here, right? Either I can put 0, 0, 0, 0, 0, 1, 0, 1, 1 or whatever. I can put only 3 values here. So at the same time I can activate only one signal. I cannot have more than one control signal to be activated, right? I cannot do that. Means degree of parallelism is really very less. Fine. So what is the alternate? We have something called partially encoded. In partially encoded, what we do is, suppose I have many control signals, like say I have total 24 control signals or whatever. So what I will do is, I will divide the control signals into some 2 to 3 parts based on their similarities or properties. So what I can do is, first 3 bit of my decoder will be used as input of this part of decoder, next all will be used as input for the next part of the decoder. So I have 2 decoder here. Instead of using a single decoder, I am using 2 decoder, but inputs are same only. So I am putting 0, 0, 0, 0, 0, 0, 0, all zeros. I am putting all zeros. In our previous case, when we have used fully encoded, what we have done is, whenever I am putting 0, 0, 0, I can activate only one signal here, right? But in this arrangement, what we can do is, when I am putting all zeros, first 3 0 will come to this decoder, next all zeros will come to this decoder. Means this 3 0 will decide which control signal from this set will be activated, and this inputs will decide which control signal from this decoder will be activated. Means at the same time I can activate 2 different control signals by putting 0, 0, 0, 0, 0, 0. You understood that? So if you need, or if it is possible, you can have more number of decoder if you need more number of control signals to be executed. Fine. So that's it for this lecture. I have already discussed what is vertical microinstruction, what is horizontal microinstruction, and the basic of microinstructions we have discussed in this video. In the next lecture, we'll discuss something more about microprogrammed control unit, where we'll see the same application, Booth's algorithm, to how to design a microprogrammed control unit for Booth's multiplication. We'll see in the next class. So thanks for watching my video.